card on this computer. Next week, you have a exam, right? And so I just wanted to kind of remind you guys, we have, this is the week 4 class notes. Mondays is going to be an exam review day. And so there's some kind of useful links and whatnot, and we'll kind of click on these in Monday's class and everything. But I also wanted to encourage you to kind of look through these problems and let me know which ones you're most interested in. I think it's maybe unlikely that we're going to be able to get through all of the problems in class, but I want to make sure to spend the time, on the problems that are of interest to the most number of students. And so I was hoping that, you would take a read through all of these and you would let me know which ones you find most interesting. So if you click on this form right here, I already have this open from earlier. Apparently it's going to reload. Thinking, oh, it kicked me off of my broadcast. But anyway, it has basically it's just a Google form. You can check which ones you find most interesting, which ones you would like me to cover in class. And then I'm going to basically go in order, right? Let me go ahead and rejoin this Zoom meeting here. In the meantime, I'll take a question here. Tommy, you're up.
Can you hear me?
Yes.
Okay, sorry. This is the first question I've asked. So I was just curious, is there going to be like a released answer key to the review document if you're not going over all the questions like during a class, or is it something that we would be completing by ourselves and then like asking the questions based on which ones we don't understand?
So it's going to be something similar to the rest of my notes, right? Where I, I'll spend time in class where, I actually give a thorough verbal explanation and everything. But then anything that I don't get to, right, I always write out a full solution and I post it on my, filled in class notes.
Okay, perfect. Thank you.
Yep, definitely. Let me see if I can't. Okay, it is sharing now. Let me see if I can't get back to my notes. Okay, maybe one more raised hand question here, and then we'll move on to today's topics. Haley, you get the last question here for the time being anyway.
I actually had a question on today's notes, if that's okay.
Yeah, definitely. Perfect segue. So yeah, let me open up really quick the pre-class notes here. What was the question that you had?
It's just kind of like a general question, but I was working on the homework and I went to the help room today and he was telling me when you have a limit to infinity of 1 over a number, it would be and the answer would be infinity, but I thought it would be 0. When there's, I don't know how to explain it.
When there's on the bottom, when there's a number over x, sometimes the limit is equal to 0 and other times it's equal to infinity, and we don't know how to decipher between the two, basically.
Yeah, so it really depends on what you're approaching, right? So it sounds like your situation is you have a number over a variable, right? So like this, 3 over x. And if you were to take the limit as x goes to infinity, then as x gets very large, right, you have 3 divided by a million, 3 divided by a billion, something like this, right? This is going to go to 0. But on the other hand, if you have the limit as x approaches 0 from either the right or the left of this, remember that this 3 over x is going to look something like this. It's kind of the one of these hyperbola sort of deals that's kind of been tilted a bit. And so if we go maybe from the right here, then this is going to go towards positive infinity. If you approach 0 from the left, right, then it's going to go down to negative infinity. So it'll really matter what you're approaching for these sorts of problems. Does that decently answer your question?
I mean, it kind of does, but we had a lot of problems where it was going to infinity, and the answer was still infinity.
I mean, did you have a situation where it shouldn't have actually been in the denominator? So that is if you had 3 divided by x to the negative 1/2 or something like this, then really, right, because of the negative exponent, this is really the same thing as 3 root x.
Yeah. Yeah, maybe that was it. I don't know.
Yeah, if you have a specific example, that would help a lot. Because right now we're just kind of talking about, a very nebulous thing.
General.
Yeah, it's on when we go over something like 686 in the pre-class notes, like those scenarios. It's kind of within that realm.
Yeah.
Okay, yeah. So I mean, certainly if you have an infinity minus infinity sort of situation, you do have to be very careful about this, because this is one of the indeterminate forms. And so we go into a little bit about how you get to this, but when this one doesn't have x going to infinity, right? It has x going to 0.
Okay.
Yeah.
So, okay, excellent. Well, why don't we go ahead and I'll do a quick skim over the pre-class notes, and then we'll get into the new problems for today. Today, we're talking about L'Hopital's rule. This is one of the very few sections in Calculus 2 where we're evaluating out limits, right? By and large, we've been doing lots of derivatives, lots of integrals, things like this, a little bit of, review of our algebra stuff, but not so much on limits. So this is one where we do get a upgraded theorem about how to evaluate out limits. And really, this comes now because it turns out there's some indeterminate forms where using properties of logarithms end up being very useful. So that's kind of why you wait until you have logarithms to bring up L'Hopital's rule. So the thing, in order to evaluate a limit using L'Hopital's rule, you need two things. First of all, you need to have a fraction. So we need to have a function on top and a function on bottom. If you don't have a fraction, you can't use L'Hopital's rule. So that's the first thing. The second thing is that it needs to be approaching one of two things. So you need to either have an indeterminate of form 0 over 0. So that is both the numerator of your fraction and the denominator, the f and the g in this case, are both approaching 0. Or they need to both be approaching infinity or negative infinity. So and in that case, you can apply L'Hopital's rule. And we've seen lots of examples in the pre-class videos here, where you take the derivative on the top and the bottom. And it turns out that the derivative, and notice that this is not the quotient rule, right? That we're just taking the derivative of the top thing, we're taking the derivative of the bottom thing. And if you take the limit of that new function, right, this new ratio here, as x goes to the exact same thing, whatever that happens to be, whatever it was back here, you do the same limit, then these limits will be equal to one another. So if this has simplified things, right, by taking the derivative, sometimes we get a simpler function. So if this actually simplifies things, well, this could be a good strategy. And so now we see a few examples of this. So we did the natural log of x divided by the square root of x. This was an infinity over an infinity situation. We saw by applying L'Hopital's rule, we can evaluate out the limit here. There are other types of indeterminate forms, right? So this 0 over 0 or infinity over infinity, these are indeterminate forms. These are things, right? If you were just kind of doing these problems naively, right? 0 divided by 0, you might be tempted to say, well, that's just 1, right? Because it's the same thing on top as it is on bottom. So they would cancel out and they give you 1. Or likewise for infinity over infinity, you would say, well, they perfectly cancel out and they give you 1. But notice that's not always the case. That's why they're called indeterminate forms, is because you need to take each one of these kind of as special cases. You need to explore it and see what the result is. So in fact, we saw in this situation, right, we had an infinity over infinity sort of situation, but they didn't perfectly cancel out and give you 1. In this case, they gave you 0. And we'll find other cases where, you get the answer 2 or 5 or 100 or negative 13, right? Each one of these needs to be handled specially. And that's why it's called an indeterminate form, is you can't just tell, just by looking at it, you can't tell, oh, it's got to be 1, right? Sadly, you can't do this. So the other indeterminate forms that need to be handled specially are things like 0 times infinity or infinity minus infinity. Infinity to the 0th power, 1 to the infinity, and 0 to the 0. All of these are indeterminate forms, and they can take on different values depending on the specifics, depending on exactly what kind of functions you have. And so each one of these, again, needs to be handled carefully. For these ones where you have exponents, right, 1 to the infinity, infinity to the 0, things like this, This is where using this natural log trick ends up being very useful. And so in order to fully use it, we need to remember a Calc 1 theorem, which says that you're allowed to push limits inside of continuous functions. So if you have a nice continuous function like f here, you can push the limit through it and you get a simpler problem, right? If you can just evaluate out this then, then you can take the result and plug that into f and you win the game. So we see that. I guess we do before that a few other examples. So this is a 0 times infinity, and we have to rewrite this as a fraction before we can apply L'Hopital's rule. Remember, in order to do L'Hopital's rule, you have to have a fraction. So you do a rewrite first in order to get a setup that you can use L'Hopital's rule for. Again, here you have to do a rewrite first in order to get a setup that you can use L'Hopital's rule for. This is the one right here that I was thinking about, where I said this bit about pushing limits inside of functions. So here we have this complicated thing where we have a variable in both the base and the exponent. Notice that this is a different problem than logarithmic differentiation, right? It doesn't say take the derivative. It says evaluate the limit. And so since we want to evaluate out the limit, right, there's not really anything to, the original problem, you can't apply a natural log on both sides because it's not an equation. It's just an expression that we're trying to evaluate. And so one strategy that you can use here is that you can give this thing a natural log. And of course, if you're going to do that, you need to also apply its inverse, right? So now you haven't really changed anything. It's like adding 5 and subtracting 5, right? Those are inverse functions, and they get back to where they started. And so, yeah, you can apply a natural log so long as you also apply an e. And now the reason why you would want to do this is that you can push this limit, right? E is a nice continuous function. If you draw a picture of that, that's a nice continuous function. So you can push this limit inside of this e. And the natural log has some wonderful properties, mainly the power rule, where you can take down that power, the 3x in this case, and now evaluate out this simpler limit. So we evaluate out this first. Here was all the work for that. Then we take the result and we plug it in back into our original problem. So notice that when we do all that work, we get 0, but the answer is not 0. Remember, we did something to it. We applied a natural log, so you also had to apply this e. So the answer was e to the 0, or 1. All right, so those are the videos in a nutshell. Let's go ahead and see what kind of questions we have out there. Yuan, what's being asked in the Q&A or chat?
Yeah, so several people is asking why don't you have 0 infinity form for the L'Hopital's rule?
A 0 infinity form.
0 to the raised to the power infinity, and there are several others. I don't like that.
So if you take 0 raised to the infinity, that this is actually well defined. So this one, can anyone maybe guess? If you take 0 and you raise it to larger and larger powers, what will the limit be? Yeah, so 0 raised to anything is just 0. And so yeah, that one actually isn't indeterminate. That one you can look at and just tell right away.
Mm-hmm.
Good. Any other questions out there?
There's a question which is not about the class. Someone's asking the average of the quiz 2.
Oh yeah, so the average of the quiz 2, it did go up substantially, I think, because like quiz 1, it was like 50% or something like this. I think this went up. Last I checked, it was like 65%. And so this is a lot more normal, I would say. So yeah, I was happy to see that. Okay, we have a few people with raised hands. Let's at least call on one person here, and then we'll continue on. We got problems to do today. So Jeff, you're up.
Thank you, Professor. I just had a question about the 0 times infinity. Is that when a trig function would come in? Because that was supposed to be a pretty absolute rule, I thought.
Yeah, so 0 times infinity, again, depending on how strong your 0 is or how strong your infinity is, you could get kind of a whole variety of things. You can have trig functions, certainly, but it's not required. So for instance, if I had one function and I'll take some maybe relatively simple examples here. So I'm going to have one function f of x to be a times, you know what, let's do 3 times x. And I'm going to take another function, g of x, to be 1 over x. And I'm going to go ahead and take the limit as x goes to infinity of the product of these two functions. So 3x and 1 over x. So in this particular case, right, you see that if you were to just, you know, let x go to infinity for each one of these, then you would have 3 times infinity for this one. And 1 over infinity is going to be 0 in this case. So this is an infinity times 0 sort of situation. Of course, this one is, you know, I made it up and it's so simple, right, that you can just look at it and say, oh, those x's cancel, right? And we're going to get 3 in this case.
Okay.
But you can't tell just by looking at an infinity times a 0 without looking at the specific functions themselves what this is going to actually equal, right? Because I could have made this 5 here, and then the answer would be 5.
Right. Okay.
And so it's it really depends on the specific functions. Of course, if I made this 5x squared, again, this is still an infinity times a 0, but now when things cancel, you get 5x, and it's infinity, right? As x gets larger and larger and larger towards infinity, this is going to be going towards infinity.
Thank you.
And so, yeah, it could be infinity, it could be 0, it could be any number in between. We have to really explore it.
Okay.
Cool. All right. Well, let's get into our new problems then for today. Jumping over here. All right. Evaluate out the following limits. So this one right here, notice that as it sits, we cannot apply L'Hopital's rule to it. So again, there's for a good number of these problems, you have to get it into its fraction form. And so let's go ahead and think about a little bit of a rewrite here that we could do in order to get it so that we could actually apply L'Hopital's rule. And in particular, when I'm looking at this, I see that we have a negative exponent. Remember, negative exponents are the same thing as secret division, right? There's really some division going on here, but it's just being hidden by this negative exponent. So yes, we could go ahead and rewrite this using up that negative exponent to move the e to the x into the denominator. And now we have a fraction. So the first thing of L'Hopital's rule is satisfied. Now, the second thing, remember, we have to have either a 0 over 0 or infinity over infinity sort of situation. So let's go ahead and check. If as x goes to infinity, let's draw quick little pictures for each one of these. Square root of x looks like this. So as x gets larger and larger and larger, it goes off to infinity. It does kind of teeter out, right? It curves a little bit, but you do get larger and larger values. So the square root does go to infinity as x gets larger and larger and larger. E to the x looks like this, right? It's getting larger and faster. And so, yes, as you plug in very, very large x's, e to the x also goes to infinity. So in this case, we do have an infinity over infinity sort of situation. So L'Hopital's rule does apply. So applying L'Hopital's rule, and quite often, you know, when I'm showing my work, whenever I use L'Hopital's rule, of course, the function here is going to change quite significantly. So I always put like a little LH over my equal sign. And I think that, you know, especially for like partial credit and stuff like this, I would recommend that you do this just so that way the graders can kind of follow what you've done and where you've applied your L'Hopital's rule. So remember, we keep the limit the same. So we're keeping it as x goes to infinity. And if we take the derivative, on the top, we get 1/2 x to the negative 1/2. And if we take the derivative on the bottom, we just get e to the x. So again, this is using the fact that the square root of x is x to the 1/2. So then we apply the power rule, right? The 1/2 comes down and we reduce our power by 1. Now, with these L'Hopital's rule problems, I always find that there's usually a little bit of cleanup, right? After you apply L'Hopital's rule, you get maybe some nasty fractions sometimes, and it's a good idea to go ahead and clean those up. So let's go ahead and do one line of simplification or so. I'm going to rewrite this 1 divided by 2 and x to the negative 1/2. Remember, that's actually in the denominator then. So I'm going to do x, and 1/2 is a square root. And we need to divide that by e to the x. So again, we have fractions over fractions. Anytime that this happens, right, I would recommend instead of dividing by the fraction, I would multiply by the reciprocal. So I would make this 1 divided by 2 root x times 1 over and e to the x. So again, instead of dividing by e to the x, we're going to go ahead and multiply by the reciprocal. Multiply by 1 over e to the x. And now we can see in the numerator, we just have a nice constant 1. 1 times 1 is 1. And in the denominator, we have this root x, which is going to be going to infinity. And we have this e to the x, which is going to be going to infinity. So we're going to have a large number times a large number, right? And whenever you have a large number times a large number, it's going to get, well, extra large, right? So this is going to be a 1 over infinity situation. So what will this limit equal? There we go. Yes, you guys got it. 0. So this is going to be equal to 0. All right. So yes, that's the final answer. That's all there is to it for this problem here. Let's pause. Any questions on this? Why don't we take one raised hand, and then I'll come back to you, Yuan. Gabriel, you're up.
Hi, yes, Professor. I just had a question. So in your second line of work in the beginning, you had 1 over 2 root x divided by e to the x. And I was just curious because I know that we typically we want to use the L'Hopital's rule in fraction form. So is it okay that is it okay to separate it out like you did in the next step, 1 over 2 root x times 1 over e to the x?
Yeah, because after that, the L'Hopital's rule is done.
Oh, okay.
Right. So we applied the L'Hopital's rule, and I have my little LH when I actually applied it. And then after that, right, we had this new limit that we needed to evaluate out. I never applied L'Hopital's rule a second time or anything like that. It was just, how do I evaluate out this thing? And then it's really up to you, yourself. How can you convince yourself that, this is going to be 1 over infinity? And I think the fraction form, and even if you have multiple fractions like this, that's fine, so long as you can convince yourself that the numerator is staying constant and the denominator is getting larger and larger and larger. And so that denominator is going to pull it to 0.
Okay, and then I guess my second question is let's just say that the 1 over 2 root x divided by e to the x, let's just say that didn't equal 0, and we would have to apply L'Hopital's rule again. Would we then have to put it back in its fractional form, 1 over 2 root x divided by e to the x, and then take the derivative of that?
Yes, very possibly. So yeah, if you still have an infinity over infinity sort of situation, or 0 over 0 situation after you applied L'Hopital's rule once, it's very possible that you need to apply L'Hopital's rule a second time.
Okay, cool. Okay, thank you.
All right, yeah, no problem. All right, Yuan, what kind of questions are out there?
I think there's a good question is asking why infinity raised to 0 is not 1, because it's a big number. Any big number raised to 0 is 1.
Back to the list of indeterminate forms. If you have infinity raised to the 0, that should be 1. I would need to think of an explicit counterexample. I guess so. Okay, this would do it. If you had, let's say f of x is equal to 2 to the x, and g of x is equal to 1 over x. And again, we want the limit as maybe x goes to infinity of f of x raised to the g of x. So notice that as x goes to infinity, this is going to be going to infinity, right? It's an exponential. And g of x, as x goes to infinity, this is going to be going to 0. So this is the infinity to the 0 form that we're talking about here. And yet, if you were to actually apply this out, right, the limit, and you plug in these specific functions, you would see 2 to the x raised to the 1 over x. What is this limit going to equal? Open it up to the class here. What will the limit of this equal? Yeah, it's going to be 2, because you have powers raised to more powers. Whenever you have powers raised to more powers, they multiply. And so this is just going to be a constant function of 2. Excuse me. And so yeah, as x gets very large, well, it's a constant function now, right? So it's just going to be 2. So yeah, here's a situation where you have an infinity raised to the 0 form, and yet it's not 1. So yeah, fun question though. All right, let's go ahead and try this next one here. Here you can see this is one of these where you have a variable in both the base and in the exponent. But remember, you kind of have to hold this, right? You have to make sure that you're solving a limit problem and you don't accidentally mistake this for a logarithmic differentiation problem, right? So we're still going to use L'Hopital's rule, but the rewrite will take a little bit of time. So in order to evaluate this out, you saw in the videos how I apply an e and a natural log kind of back to back, and we have a kind of a separate problem to solve. And so I'd like to do something similar here in a slightly different format, maybe just to kind of expose you guys to different ways of solving this. And I'm just going to outright consider a separate problem here. So I'm going to consider the limit as x goes to 0 from the right, and I'm going to add in this natural log here. So I've added in this natural log. And of course, this is going to give me a different answer. I'm considering a different problem. And so I get a different answer. And so I'll have to spend some time at the end figuring out, well, how far am I off by here? And so, okay, but since this natural log is here, let's go ahead and use this. Remember, with the natural log here, we can apply the power rule for logarithms. And so I can go ahead and I can bring down the power. Now, this is very close to a fraction form, right? So I'm going to go ahead and write this one more time here. The limit as x goes to 0 from the right of 2 natural log of cosine of x divided by x. All right, so now let's go ahead and check and make sure that this is actually in its fraction form here. All right, welcome back. We're here. So what I was just saying is that we need to make sure that this is actually something that we can apply L'Hopital's rule to, right? So let's double check here. When I plug in 0, right, we're going to have the natural log of, and cosine of 0 is 1, right? So this is going to be the natural log of 1. Well, that's the same thing as 0. So that's on top. For the denominator, as we get closer and closer to 0, well, it's just an x down there. So this is, of course, going to be 0. All right, so this is going to be a 0 over 0 situation. And so we have the two things that L'Hopital's rule needs. We have a fraction, and we have in one of these two indeterminate forms, either 0 over 0 or infinity over infinity. And so let's go ahead and apply L'Hopital's rule to this. And when we apply L'Hopital's rule, again, we take the derivative of the top, we take the derivative of the bottom. Notice that the derivative of the bottom is so very nice, right? It's just x. And in the numerator, when we take the derivative of this, well, we have 1 divided by cosine times the derivative of the inside. The derivative of cosine is going to be negative sine. Oh, I see. The chat. Sorry, guys.
What's up?
Let's go ahead and plug this in, right? So the limit as x goes to 0, we have a sine divided by cosine in this case. Let's go ahead and not skip steps here. So this is going to be negative 2 sine divided by cosine. And as x goes to 0, we have 0 divided by, and cosine of 0 is 1. So this is going to be 0 divided by 1, 0. Okay, I see there's some raised hands. So we'll get to that in just 1 second. But remember, I made up a new problem. This problem that I just solved right here is different than what I was originally given. I need to solve the problem that I was originally given. And if we want to apply a logarithm, right? If we want to pull the logarithm from the stars and give it to this function, right? We've changed something. And well, how much have we changed it by? Well, you need to give it the inverse as well. So the final answer is going to be e to the 0. and e to the 0 is going to be 1. So again, one last time here where I'll go through kind of all the formalness of this. And then, you know, in the future, kind of we'll just remember to apply this e at the end. So really what we are doing here is that similarly to how you add 5 and subtract 5, right? Adding 5 and subtracting 5 is just a fancy way of, you know, doing nothing. You know, these are inverse functions. This is 0 really. We're going to do the same sort of deal where we apply an e and a natural log. Because again, these are just inverse functions here. So they cancel out and you're just left with kind of the original thing. We then push the limit inside of the e. The natural log of cosine of x raised to the 2 over x. Because e is a continuous function, we're allowed to do that. And then we solve this problem right here. This is just what I spent a lot of time solving. We found out that the answer was 0. So we plug that in to this e raised to the stuff, right? And that's why our final answer is 1. So our final answer after all is said and done is 1. All right, with that, let's go ahead and take some questions. I'll look at the raised hands first here and then throw it over to you, Yuan, and see what's going on in the Q&A. Let's see. Ajuan, you're up.
All right, can you hear me?
Yes, sure can.
All right, so okay, I was looking. I'm like looking over like most of the like the equation that you're doing and like the problems that you're doing. So like, will there ever be a time where like not equals 1, or it'll be like you know equals 2, or you know any other number except 1? Would there ever be a case like that?
Yeah, for sure. In fact, right, this little mini example that I came up with right here was a time where it was equal to 2.
Okay. So is it matter whole numbers, or is it just like decimals as well, or any number, any real number?
You could do any number. Sometimes they get, you know, if you want an especially ugly answer, sometimes you have to start with an especially ugly, you know, question.
Okay, yeah.
You need maybe a difficult question or something with a square root or with, you know, maybe some trig functions or stuff like this. So yeah, you could get it to give you an ugly answer, but for the most part, we like to, you know, whole numbers are nice if, you know, you can get them to work out like that.
Okay, cool. Thank you. I just want to.
Yeah, I also wanted to point out this was the first example that we did here. We got 0, so that was not 1.
Okay, cool. I meant to say 1 and 0. That's what I meant to say.
Okay.
So.
Fair enough. All right, awesome. Let's call on one more person here. Justin, you're up.
Hey, good afternoon, Professor. I just got a quick question.
Yes.
I got lost in regards to the -2 sine x over cosine. Where did that 0 and 1 come from out of that?
Yes. So we were still, remember our overall goal is to evaluate this limit as x goes to 0. And so we've been itching you, just like in our calculus 1 days, where you have these problems, you know, like the limit as x approaches 3 of x squared minus 9 divided by x minus 3, right? You're itching to plug in a 3 everywhere you see an x. But right now, when you do that, you divide by 0 and there's an issue with that, right? So we've been itching to plug in 0 everywhere we see an x, because after all, that's what our limit wants to be evaluated out at, right? X going to 0. And so now, you know, after each time we apply L'Hopital's rule and whatnot, we have to plug in 0 again for x to see if we're still in one of these indeterminate forms like we were originally, right? We had a 0 over 0 situation. So that division by 0 says you can't just leave it like that. You have to do something to it. So the question is, are we still in one of these indeterminate forms, or do we actually know what the answer is finally? And so we applied L'Hopital's rule. We took our derivatives, all that sort of stuff. And then that 0 over 1 is where we went to, again, try to plug in 0 everywhere we see an x. So when we do that, right, plug in 0 on the top, well, sine of 0 is 0. Who cares about that -2, right? -2 times 0 is still 0. And in the denominator, right, we have cosine. Cosine of 0 is 1. And again, you can verify all these things with our calculator and whatnot. But cosine of 0 is 1. And so you get 0 divided by 1. Finally, we're not dividing by 0. right? And so if you take 0 and you divide it by 1, you just get 0.
Okay, got it. That makes sense. Thank you.
Super. Yeah, no problem. Let's at least take one question from the Q&A as well. Yuan, what do we got here?
Yeah. So here you use the ln function. So usually people ask is, when did you use this kind of method? Or can we always use this kind of method?
Yeah, great question. So how do we know when we need to apply a natural log, right? And the answer is kind of similar to when you'd use logarithmic differentiation, except for remember, you're not taking a derivative in this case. But the main, kind of bells and whistles that are going off is whenever you see a variable in both the base and the exponent, that's when applying a natural log, either, just on both sides of an equation, like with logarithmic differentiation. Remember, you have an equation, you usually have something like y equals whatever, 2x raised to the x or something like this. Then you can apply a natural log on both sides of the equation. Or in this case, where we just have an expression, right? We don't have an equal sign or anything like this. We just want to evaluate this. You can apply a natural log so long as you also apply its inverse, right? And that's why that e will, need to come into the problem at some point earlier or later. So, here I do the natural log, I apply that, I spend a lot of time with it. Of course, that altered my final answer, and I need to change it back. So in order to change it back, in order to undo that natural log business, you need to apply an e at the very end. But yes, the indicator is the same, variables in the base and the exponent. That's a great question. All right. All of our the tech issue did not help our situation. I would like to maybe skip to my last problem here, and then I don't think this should take the rest of the time by any means, but I would like to stare at this problem here because it's a different flavor of question. And I would like to give you guys maybe 60 or 90 seconds. You can see that I've labeled this. This was a problem that came up on the spring 2018 exam 1, and I labeled this as a cruel problem. So I'd like you to please take 60 or 90 seconds to try to solve this. It was a multiple choice problem. I've given you the exact multiple choice answers that they gave then, but please try to solve this problem for me. Give you guys 60 seconds or so. I'll answer some questions in Q&A and chat and whatnot, and then we'll spoil the surprise together. All right, let's talk about this problem here for a minute. The first thing is that we see a variable in both our base and our exponent, right? And so if you go too fast, right, you start applying the natural log and all this sort of stuff, and you can spin your wheels actually for a while going down this path. The problem with this one is that when you take the limit as x goes to 0 from the right, what do we get? Well, as x goes to 0 from the right, you have inside here, 1 over x looks like this. So as x approaches 0 from the right, we get positive infinity. For the natural log, so if I was to draw a picture of the natural log really quick, as x approaches 0 from the right, it goes down towards negative infinity. So in this case, we get infinity raised to the negative infinity. Is this an indeterminate form? Was this on our list? The answer is sadly no. And so even if you apply the log and all this sort of stuff, you'll see that you don't get L'Hopital's rule sort of situation. You won't get one of these 0 over zeros or infinity over infinities. So in this case, we get a very, very large number raised to a very, very negative number, negatively large. So in this case, right, if you use up that negative exponent, right, you're going to get infinity raised to the infinity in the denominator. So if you take 1,000,000 and you raise it to the millionth power, or 1,000,000,000 raised to the billionth power, large numbers raised to a very, very large number, well, it's going to stay very, very large. So you get a 1 over infinity sort of situation. And what is the final answer? 0. So yeah, that's why I labeled this as kind of a cruel problem, because the majority of the questions that we see in Calculus 2 here, right, if you have a limit question, remember, we haven't really gotten any other limit problems here in Calculus 2. And so the expectation that the students had was like that you needed to apply L'Hopital's rule, that this was testing you, can you apply L'Hopital's rule? But actually, this wasn't testing you, can you apply L'Hopital's rule? It was testing you on whether you should or shouldn't apply L'Hopital's rule, right? What were the exact, kind of, when do you need to apply L'Hopital's rule? When are the hypotheses met versus when can you just, plug in your values and kind of see what it goes to? So because this wasn't an indeterminate form, you didn't need to use L'Hopital's rule. And in fact, you can spend a lot of time going down a bad path if you do try to use L'Hopital's rule. So that's why I thought that this one was kind of an interesting problem. Once you know what to do, it's very, very fast, but making sure that, you don't even apply L'Hopital's rule to this, you just evaluate it as is. It's an interesting problem here. Let's take a question, and then I'd like to do at least one more problem here. So I'll just take one question, and then let's do a little bit more. So Alexandra, you got the floor.
Hi. So I have a question. Is it like infinity, like with the power of negative infinity?
Mm-hmm.
Because like when you're putting in 0, you like in the 1 over x, you're like not putting in 0, but you're putting something like a little bit bigger than that, like 0.01 or whatever.
Exactly.
But I just don't get negative infinity for the L, and because isn't it if you plug in like 0, it's like doesn't let you. It's like an error or whatever, like undefined.
And it's the same thing if you just try to plug in 0 into this, right? You get 1 divided by 0, and that's undefined, right? So with all of these limits, you have to be very careful about when can you actually plug things in, right? Because if you just try to plug in 0, right, again, it's undefined. 1 divided by 0 is not well defined. But we can talk about what it approaches as x approaches 0. So like if you plugged in 0.1 or 0.01 or 0.001 or something like this, right? You approach 0, what happens to the function? So like you said, with 1 over x, as you plug in smaller and smaller things, closer and closer to 0, that this gets larger and larger, it's going towards infinity. And for the natural log, if you plug in things, right? So here's my natural log function. If you plug in 0.1 or 0.01 or 0.001, right? Again, you can't really plug in 0 into this thing, but you can plug in values closer and closer to 0, and you'll see that the natural log goes down, 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 down to negative infinity. Does that kind of make sense?
Okay, so yeah, so even for like if we have a limit and we have like a going to 0 or whatever, even if it is like the natural log, you'd still plug in like something close to 0, not 0.
Exactly. Yep.
Okay.
No matter what the function is, whether it's a log function, whether it's an e, whether it's, a rational function like 1 over x sort of deal. Again, with all of these, you're plugging in things very, very close to 0, but they're not quite 0.
Okay. Thank you.
Yeah, of course. All right. With 1 minute to go, let's look at, well, we've already done this. Let's maybe just do this one here. This is one where I believe we're going to need to apply L'Hopital's rule twice. So I'm going to speed through this one a little bit, and then we'll stick around after to answer any questions. So this is one that does appear or something like it in web work.
Just one thing, can I ask a question? Because someone said I said that opposite as you said, because I didn't hear what you said. It's log infinity is just infinity, right?
Log infinity? Yeah, that's true.
Yeah. Okay.
Yeah, the problem is this one we're not going to infinity, right? So for this one right here, the limit as x approaches 0. So that's why it's negative infinity, right? If this had been going off to infinity, that would be a different question.
Okay, I see.
So if I was to just plug in infinity here, we would have the fifth root of x. Well, this goes to infinity, albeit a bit slowly. And we have the natural log squared of x. So, right, so again, as x goes to infinity, this will go into infinity. So we have an infinity over infinity situation. We can apply L'Hopital's rule. So let's go ahead and do that. Again, I'll be speeding through this one a little bit. The fifth root of x is the same thing as x to the 1/5. We're going to go ahead and bring down that exponent, reduce our power by 1. And in the denominator here, we have to be a bit careful, right? This is the natural log inside of the squaring function. So when I take the derivative of this, the 2 comes down, reduce our power by 1, leave the inside alone. Then we multiply by the derivative of the inside. And so the derivative of the natural log is 1 over x. Again, we're going to take a line to simplify this, to clean up a little bit. Let's see, we have a 1/5 and a 2, so that's going to be a 1/10 altogether, or I can put a 10 in the denominator. It looks like I'm dividing by a fraction, so remember I can go ahead and multiply by the reciprocal of this. So I'm going to flip this, multiply by x over 1 rather than dividing by 1 over x. We still have a natural log down here. And in fact, let's use up this negative exponent here and push this down into the denominator. And so, okay, we've done a little bit of cleanup. I can see that we can cancel a little bit, right? We have x to the 1 here, and we have x to the 4/5 in the denominator. So remember, some of this is going to cancel out, but there's more in the numerator than there is in the denominator. In fact, there's 1/5 more. There's 1/5 more x's in the numerator than there is in the denominator. So there's some left over. And now when you plug in infinity, you see that you get infinity divided by infinity. And the reason why I wanted to make sure to do this problem, or to at very least start it here, is that whenever you get this, right, it feels like you haven't made a lot of progress, right? Because we started off with infinity over infinity. And after doing L'Hopital's rule, we still have infinity over infinity. And so whenever that happens, you have to pause and question and make sure that you're going down the correct path, because you could use L'Hopital's rule again on this. But the question is, to what end, right? Will this actually simplify down and give me some good answer? Or am I just going to do this, 10 times and I never get my result? And so we need to look at the problem maybe that we started off with and compare it to the problem that we have and see if it's looking any simpler, right? Are we actually making progress? And in this case right here, I would say, yes, we are making progress. Sorry, I shouldn't be writing this L'Hopital's rule here because we only applied it in that first step there. The other ones were just simplifications. But yes, we originally had the natural log squared in the denominator. Now we just have natural log to the first in the denominator. So I'm hoping that if we use L'Hopital's rule one more time, here's where I'll do it, that now we will actually get rid of all of the natural logs, right? So this will just become 1 over x here. And again, you'll have a 1/5 x to the negative 4/5. And now when we go to simplify, so this is now 1/50th in the denominator here. This is going to be, let's see, dividing by 1 over x is the same thing as multiplying by x over 1. And let's put that x to the negative 4/5 in the denominator using up its negative sign. And so now we can see that these things are going to cancel a bit, right? And we're going to be left with the limit as x goes to infinity of 1/50th times x to the 1/5. Again, there's 1/5 more x's in the numerator than there is in the denominator. Now, right, when you plug in infinity, you have infinity on top and, well, 50 on bottom. 50 is no match for infinity, right? This is going to go to infinity. So this right here, the final answer is infinity. This thing as x goes to infinity, this the numerator will win out. This will go to infinity here. All right, that's probably a good place for us to end. Thank you guys for sticking around with me. I hope you have a wonderful weekend and all that. We'll stick around for a little bit here. If there are any one-on-one questions or questions that you have about any of this stuff, please feel free to ask them. Again, I have office hours today, 4 to 5. So if we don't get to all of them, 4 to 5 today, I have office hours. Please come and hang out. All right, let's call on some folks who have raised hands. Chris, we haven't heard from you today.
Yeah, I have a couple of questions.
Absolutely. What's up?
Yeah. So first of all, starting with the glitch, will that affect our attendance points?
No. So we'll look at both of them and anyone who attended. So yeah, we'll reconcile it all.
Okay. And second of all, like, do you know how many questions are there going to be on the exam next week on the 11th? And it's from 7 to 8, right?
8 to 9, I believe. But
what?
Now you have me paranoid. Check the syllabus.
Okay, I thought it was from 7 to 8. I don't know.
Well, it's a good thing that you're bringing it up now. Yeah, double check the syllabus. I'm pretty sure that's from 8 to 9, but now you got me paranoid, right? And it's unlucky to ever say the wrong time.
Yeah, right. Because then it messes everything up.
Exactly.
And right. And my so what kind of questions can we expect? Can we expect like easy peasy points, like multiple choice, like hey, like the one that we did on example 14 and example, wait, what was it? Example 14, 16 and 13, A and B, like and then you know, how about the solid soft revolution, and then like all the other stuff that we studied up until to this point, because you said that it's broken into 2 parts now. That confuses me, because exam 1 is broken into 2 parts, and so I'm like confused. So I'm like, wait, so everything we learned will be over there, or like just half of it, like and how many questions are there exactly? So you know, I'm going through all these questions in my mind.
Sure. I'm not exactly sure what you mean by the exam will be broken into 2 parts. It's just 1 part. And so hopefully that's reassuring to you. As of right now, we have 12 questions. 4 are standard response, 4 are multiple choice, 4 are true false. It does cover all of chapters 5 and 6. So yes, there will be stuff with solids of revolution, very possibly work, you know, all the stuff from chapter 6. You know, 6.1 is not included because again, we didn't cover that this semester. But 6.2, 3, 4, 5, 6, all the way up to this stuff today, 6.8 L'Hopital's rule stuff. That will be the content on the exam. Now there will be a mixture of difficulty level problems. And I think when you say something's easy, that's very relative. If it's easy for you, it's not necessarily easy for everyone. And so you have to be kind of hard, right? How do you measure easy versus hard questions? But there will be, last I checked anyway, there'll be questions that you will have seen, you know, very similar things to, and maybe so that could be a somewhat definition for easy, like have you experienced a similar question either on the quiz or the homeworks or things like this. So yes, you will have seen you know, similar questions to a fair number of these things, right? We're not